In this video, we're going to talk about the PID controller and its transformation from a single station device to what it has evolved into today. We're going to explain why PID controllers are used in industrial processes instead of simple on-off controllers. We'll illustrate how controller settings called proportional, integral, and derivative affect different processes under control. We'll also provide an overview of the very important activity called controller tuning. Let's start with a discussion about home temperature control, as it's familiar to lots of people. This house has a furnace that distributes heat throughout, and a wall-mounted controller called a thermostat. The thermostat has a sensor that measures the house temperature and compares that measurement to an adjustable set point. If the room temperature is below the set point, the furnace is turned on. When the room temperature increases above the set point, the furnace turns off. This type of control is referred to as on-off or bang-bang control. Here's a plot of what the room temperature does over a period of time as the furnace turns on and off. As you can see, the temperature is not exactly held at the set point of 70 degrees Fahrenheit, but cycles above and below the set point. On-off control may be okay for your house, but it is not okay for industrial processes or motion control. Let's look at an example of tank level control to explain why. The valve fills the tank as the pump drains it. If the valve is operated with on-off control, the water will fluctuate around the 50% set point. For our purpose, let's say the fluctuation is plus or minus 10%. In most industrial applications, this fluctuation around the set point is not acceptable. Okay, well, what if it's possible to throttle the valve and place it in any position between on and off? Now we can move on to talking about a PID controller. P stands for proportional, I stands for integral, and D stands for derivative. Because every process responds differently, the PID controller determines how much and how quickly correction is applied by using varying amounts of proportional, integral, and derivative action. Each block contributes a unique signal that is added together to create the controller output signal. Let's look at how a PID controller fits into a feedback control loop. The controller is responsible for ensuring that the process remains as close to the desired value as possible, regardless of various disruptions. The controller compares the transmitter process variable, or PV signal, and the set point. Based on that comparison, the controller produces an output signal to operate the final control element. This PID controller output is capable of operating the final control element over its entire 100% range. Most modern PID controllers are part of a PLC or DCS and are created in the program control logic using block commands. Before PLCs came along, a PID controller was a standalone device, responsible for controlling one loop. A control room would have dozens or hundreds of standalone controllers mounted on a panel. There are still many standalone PID controllers being manufactured and used today. Okay, let's get back and talk about what each of the P, I, and D components of the PID controller does. Remember earlier we said that the PID controller is responsible for ensuring that the process remains as close to the set point as possible, regardless of various disruptions. Let's refer to the difference between the process variable and the set point as the error signal. The proportional block creates an output signal proportional to the magnitude of the error signal. Unfortunately, the closer you get to the set point, the less it pushes. Eventually, the process just runs continuously close to the set point, but not quite there. That's when integral jumps in. The integral block creates an output proportional to the duration and magnitude of the error signal. The longer the error and the greater the amount, the larger the integral output. As long as an error exists, integral action will continue. The derivative block creates an output signal proportional to the rate of change of the error signal. The faster the error changes, the larger the derivative output. Derivative control looks ahead to see what the error will be in the future and contributes to the controller output accordingly. That brings us to a term called controller tuning. We said earlier that every process responds differently and that the PID controller determines how much and how quickly correction is applied by adjusting proportional, integral, and derivative action. Controller tuning involves correctly setting the controller P, I, and D values for specific process requirements. Interestingly, the correct settings achieved by controller tuning can differ vastly between processes because of specific requirements. For example, after the controller has been tuned, a set-point bump of 1% in a tank-level control produces a quarter-wave damped response. This type of response may be suitable in a tank-level process, but could be disastrous in a motion control process. There are many different manual methods for tuning a controller that involves observing the process response after inflicting controller set-point changes. One method involves increasing the amount of set-point change and repeating the procedure until the process enters a state of steady-state oscillation. This method of tuning produces adequate results, but is often impractical in many applications. For example, how practical is it to force the fluid level in a large tank to reach a steady-state oscillation? Most process controllers, PLC, and DCS loop controllers sold today have auto-tuning capability. The PID controller learns how the process responds to a change in set point and suggested PID settings. Regardless of whether the initial PID parameters are derived from the manual or auto-tuning methods, additional tweaking is often required by seasoned automation professionals to get the response desired. Let's review. An on-off or bang-bang controller has only two output conditions and switches abruptly between these two conditions. In a PID controller, P stands for proportional, I stands for integral, and D stands for derivative. The PID controller is responsible for ensuring that the process remains as close to the desired value as possible, regardless of various disruptions. The PID controller determines how much and how quickly correction is applied by using varying amounts of P, I, and D action. The proportional block creates an output signal proportional to the magnitude of the error signal. The integral block creates an output proportional to the duration and magnitude of the error signal. The derivative block creates an output signal proportional to the rate of change of the error signal. Controller tuning involves correctly setting the controller P, I, and D values for specific process requirements, either manually or automatically. Want to learn PLC programming in an easy-to-understand format and take your career to the next level? Head on over to realpars.com.